Sorry, by
Rotational
okay.
rotation.
Let's yeah. Angular momentum. Angular momentum principle says that the momentum of the two systems are conserved. This is a bit deceptive considering there not being any angulared. That wasn't a word. Sorry, I was flipping a page. So we're okay. That's the name of the unit, and so that's this is where we learn. It's the collision principle, collision concept. It's just the concept of collisions. I thought that was called the angular momentum principle. Okay, sorry. So to start, yeah, everyone knows about inelastic collisions, right?
Yes.
Cool.
Yeah.
So this is an inelastic collision, meaning the velocities are not conserved. In fact, the final velocity will be way less than the original velocity. And we can find the velocity of the first one. I'm just going to skip all the previous stuff. So we can find the velocity of the first one by doing the square root of 2gh. This comes from the energy principle, 1/2 mv squared equals mgh. Dividing all that junk out gives us v equals square root of 2gh. Using the conservation of momentum, we know the original momentums will be equal to the final momentums, and because it's an inelastic collision, we know the final velocities will be equal. This was covered in the lecture, but how I did it is I'm just going through it again, just to make it solidified. Oops. Solving for the final velocity for both of them is just the mass of the first one divided by the sum of the masses multiplied by the original velocity. And because the second putty ball is 2 times the mass of the first one, the total mass would be three times the mass of the first one, giving a final velocity of 1/3 times the initial velocity. Am I moving too fast?
Nope.
No, perfect speed. You're killing it.
Doing good.
Okay, cool. So using this velocity for the initial velocity as for the not system, but the situation, I guess, that we're going through now. So I'm setting the initial position at the point of the collision and the final position at the point of the highest point. So we know, due to the energy principle, the change of kinetic energy plus the change in internal energy, which is equal to the work, and the system is everything, so there's no work. The kinetic energies are, I wasn't going anywhere with that. The potential energies are all gravitational. We know the final kinetic energy is going to be 0. The initial kinetic energy is just 1/2 mv squared. I'll substitute stuff in later. And the final potential energy is mgh because it's all gravitational. The initial gravitational potential energy is 0 because it's at the very bottom. We've done this sort of problem a lot of times. So solving, we get that the gravitational potential equals the kinetic energy, and substituting everything in. So for the mass, I substituted in 3m. I did that here as well. For velocity, I substituted in the previous velocity, 1/3 times v1 initial, and so that's 1/3 v initial squared. Doing some algebra, I simplified down. I divided out the 3 to get v squared over 18 equals mgh. And solving for h, which is what we want to do, I got v squared over 18g. Now, the problem says that we need to use the variables provided and g, which is a problem because now we have velocity. But in the very beginning, we said velocity was equal to the square root of 2gh. They're the same velocities, which so v squared is equal to 2gh. H in this instance is the initial height, and gravity cancels out. 2 over 18 is 9. So the final height is equal to the initial height over 9. And that is the answer. Just over 5 minutes.
Thank you, Professor.
Does this make sense?
Yes.
Yes.
It
Not o-
definitely does. I
not
need to
only-
work it out.
Okay, yeah. Not only does it... Sorry, I'm just speeding through this because I have an election watch party that I need to get to.
Okay.
No, but... Yeah.
This pulls a lot from like the other stuff we learned.
Yes,
Really
it does,
nice.
which is why... So
Yeah.
doing it on my own, I was able to finish it relatively quickly. Like, but... And which is why I feel pretty comfortable speeding through it. Or at least walking you guys through it, because... it's not the most complicated thing we've ever seen, and a lot of it's pretty straightforward.
Mm-hmm.
That being said, it is a new topic, and so I could have gotten something wrong. I very well could have, either algebraically or conceptually. So if you guys disagree with me, please say something. I was doing a lot of
Okay.
hand motions there, but you couldn't see because I am just a discombobulated voice.
I
You guys
just
never
have
told me how your meetup went.
What meetup?
Like you
ice
guys
cream.
like, yeah.
Ice cream, it was fun. It was ginger.
Oh, yes. It was good ice cream. Chris didn't show up.
It was pretty chill.
Mm-hmm.
It was nice.
Sounds fun.
I have one question. So where you have like v final equals, so it's like towards the top where you have like v final equals m1 over m1 plus m2.
Mm-hmm.
So I know there's a lot of like equations in the lecture notes. There's like one v final is like mass 1 minus m2 over the sum of the masses. Like how do you decide like which formula I
So-
guess to use for v final?
So the one that you mentioned, mass 1 minus mass 2 divided by mass 1 times, or plus mass 2,
Yeah.
that was from an elastic collision. This is an inelastic collision,
Oh.
which reduces the number of equations that we have to keep track of.
Okay.
Mm-hmm.
And then there's another one that's 2m over m1 plus m2. Is that one also elastic?
That one is also elastic. And
Okay, yeah.
that
got it.
comes... Oh gosh, I want to say directly from... No. That was this... So, the one that you mentioned, so elastic collisions... So a good example of an elastic collision is one ball, like pool balls. So one ball hits
Yeah.
another ball, the pool ball stops, the first ball has the same velocity. Now that's when both of them have the same mass, the velocities flip. So if one's stationary and one is moving at velocity v, when they collide, the stationary one will start moving at velocity v, and the moving one will then go to rest. When they're not the same mass, their velocities are in proportion to each other, but they do still kind of flip. So essentially the bigger one will have less of a change than the smaller one does, which makes sense because their masses are different. How they I'm just trying to read. I'm trying to figure out how they derive these equations. For the recitation, I just stole the equations, but
Yeah.
but
I think I was gonna go ahead.
big important thing is to note that when to use each equation is specifically when they say it's either elastic or inelastic. And
Okay.
you can also derive whether it is elastic or inelastic from the energy principle, because the definition says that elastic collisions have preserved kinetic energies. Like the kinetic final is equal to the kinetic initial. Inelastics do not. The final one will be less than the initial one. like in this scenario. So the final velocity is actually 1/3 of the initial velocity.
Because there's a change in internal energy involved.
Mm-hmm.
Okay, yeah.
If you want to use the energy principle, if you want to use the momentum principle, it's because the masses increased while velocity stayed the same.
Okay.
Mm-hmm.
Sorry, 1 sec. I'm writing down the justification.
You guys are A-okay.
You're already on the justification? My god. Okay.
Oh, I have the entire thing done. I didn't do problem 2 because I was so confident with this one. And problem 2 is the same thing, except problem 2 is elastic. So I'm going to leave that up to you guys if you guys want to do it.
Yeah, I'll probably do it. I need the practice.
I might dip out, though.
I'll probably do it, but probably not now.
Mm-hmm.
Yeah, I was about to say, I was like, I'll probably do it, but like some other day after my exam tomorrow.
Oh, you got an exam tomorrow? Jeez.
Yeah.
Which class?
Math 261.
Fun!
Yeah,
Um,
it's gonna be a blast.
I'm about to have my 162 exam next week.
Ooh, good luck. Gonna kill it.
Calc 2 in college is not fun. I should have taken it at community college.
Dude, I had so much fun in Calc 2.
No.
I remember one of the tests, I forgot an equation, and I was kind of panicking because I really needed that equation. So I got done with the entire rest of the test, and I looked at the time. I still had about 30 minutes left, so I spent the entire rest of the time deriving the equation that I needed.
Oh my god.
And I wrote a proof for the equation that I came up with.
Oh my god.
On the back of one of the pages.
You had so much fun. You just like,
You deserve an
this
award.
is how I got this, guys. Like, let me just show you how I got it. Here you go. Turn it in with a smile on your face. Like, this is mine. Here you go. Gold star.
That was fun. It was a fun test.
Beautiful.
There was also, I think I was taking a test, and it was on a Wednesday, and I play pool on Wednesdays, and so I didn't want my friends to get way better than me at pool, so I sped through the test so I could go play pool with them, because they could only play pool for a little bit.
Wow.
Seems like a smart decision.
How'd you do on the test?
I got a perfect.
Oh my god.
Thank you.
Flex.
So I mean,
Perfect.
I guess it kind of worked out.
Perfect.
I won the pool game as well.
Wow. Got a double flex.
Oh, math is fun.
I can't imagine getting a perfect in that class.
Yeah. On a college exam.
Well, if you randomly guess, you have a non-zero chance of it happening.
Well, you see, this year they decided to have
Never
free
mind.
response by
These-
lab math,
Those would suck. I'm gonna be honest. Those.
no partial credit.
Mhm.
Hate those.
Yeah, those suck.
People are getting less than 10%. It's so sad.
Oof.
That is a rip. By the way, so how do we feel about this answer? H/9.
Confident.
I'm good.
Feeling good. Feeling good.
Did I even do my math
What
right?
did you do for a separate poem? I can't really think of a.
Oh,
We
I
have to do a separate problem.
just did two carts hitting each other.
Just like on a flat plane.
Yeah.
Okay.
H/9 seems weird, but
I don't think it does.
I mean, it's sort of like the lectures that we had. We had like, I think it was. But that was so much one of the lecture problems. I don't think it's. I
mean,
don't think it's wrong. I think
okay.
it's reasonable.
Well, if you guys are willing to stand by me, then so am I. Nice job, guys.
Beautiful.
Good work
Ooh.
this